A fine good morning to everyone. This is Jakadipti of Branch Aeronautical Engineering, Semester 6, roll number 239582114. Today I am here to give presentation on behalf of AAT Tech Talk. The subject is finite element methods. The topic which I have chosen is estimation of load vector stresses for two-dimensional axis symmetry elements. Now getting into the introduction of this topic, in many engineering problems structures exhibit rotating symmetry about a central axis. Examples include pressure vessels, pipes, nozzles, shafts, tanks, rocket casings and turbine components. For such geometries, a full three-dimensional analysis is computationally expensive and often unnecessary. Instead, these problems can be efficiently modeled using two-dimensional axis symmetric finite elements, which significantly reduces computational effort while maintaining accuracy. In axis symmetry analysis, the geometry, material properties, loading conditions and boundary conditions are assumed to be symmetric about an axis of rotation. The estimation of the load vector and stresses is a critical step in the finite element formulation of such problems, as it directly affects the accuracy of displacement and stress prediction. Axis symmetry elements are used to model structures with rotational symmetry about a central axis. They simplify three-dimensional problems into two-dimensional analysis by leveraging symmetry. Understanding load vector estimation and stress calculation is essential for accurate structural analysis. Now, fundamental concept of axis symmetry. An axis symmetry problem exhibits identical geometry loads and boundary conditions around a central axis. The primary coordinates are radial, axial, and circumferential. The analysis assumes variables are independent of the circumferential coordinates, simplifying the problem to 2D. The concept includes an axis symmetry problem is defined in the RZ plane, where R is the radial component, Z is the axial coordinate. Although the finite element mesh is two-dimensional, the actual structure is three-dimensional due to rotation above the axis. Each node in the 2D mesh represents a circular ring in 3D space. Degrees of freedom. Each node in an asymmetric element has radial displacement UR, axial displacement UZ. Types of loads in axis symmetry analysis. Loads can include pressure, axial forces, or distributed loads acting on the structure. These loads are often expressed in terms of their components along the radial and axial directions. Proper load representation is critical for accurate estimation of the load vector. The governing equation is the finite element equilibrium equation is Ku is equals to F, where K is the global stiffness matrix, U is the nodal displacement vector, F is the global load vector. Accurate estimation of the load vector and stress component is essential to solve this system reliably. Estimation of load vector. The load vector represents external forces acting on the structure. In axis symmetry elements, loads must account for circumferential effect due to revolution. The types of loads are body forces, surface tractions, and point loads. First one, body forces, due to gravity or centrifugal effects, then act throughout the volume. Then coming to surface tractions, pressure loads, distributed forces on boundaries, and then point loads, applied at specific nodes, less common in axisymmetric analysis. Body force load vector are for a axisymmetry element. The body force load vector is given by Fb is equal to the integration of complete volume n to the power t, which is n transpose b into dv. Considering axisymmetry, dv is equals to 2 pi r dA. Thus, the force which is equals to the integration of complete area n transpose b 2 pi r dA, where n is a shape function matrix, d is a body force vector, then r is a radial distance. Displacement and strain in axisymmetry elements. Displacement are characterized by radial UR and axial UZ and circumferential U theta components. Strain components are derived from displacement gradients. Considering the symmetry, compatibility conditions ensures the strain are consistent with the displacement within the element. Then coming to surface traction load vector. Surface tractions such as internal pressures are common in axisymmetric problems where force of the surface is equal to the complete integration of surface in transpose TdS, where asymmetric conditions ds is equal to 2 pi r dl, thus complete force of surface is equal to integration of L n transpose T 2 pi r dl. This formulation ensures correct circumferential force distribution. Stress estimation in axisymmetry elements. Once nodal displacements are obtained, stresses are computed using strain displacement and consecutive relations. The stress component in axisymmetry problems are the primary stress includes radial sigma r, then axial sigma z, and hoop sigma theta stresses. The stresses are related to strain through consecutive relations, typically Hooke's law for elastic materials. Accurate stress estimation requires integrating these relations over the element volumes. The strain components are the axisymmetry analysis. 4 strain components are considered: radial strain, axial strain, hoop strain, and shear strain. Radial strain is equals to epsilon naught E is equals to dou ur by dou r, where axial strain epsilon naught z is equals to dou uz by dou z. Then coming to hoop strain, epsilon naught theta is equals to ur by r, and then shear strain where gamma rz is equals to dou ur by dou z plus dou uz by dou r. Then estimation of load vector. The load vector is obtained by integrating the external loads over the element's area or volume. For pressure loads, the integration considers the element's geometry and load distribution. Numerical integration techniques like Gaussian quadrature are often employed for accuracy. Strain displacement relation includes epsilon naught is equals to bq, where b is the strain displacement matrix and q is the nodal displacement matrix. Then coming to stress strain relation, assuming linear elastic isotropic material behavior, sigma is equals to d into epsilon naught, where d is the constitutive matrix and sigma is the stress vector. Stress components includes radial stress, axial stress, hoop stress, and shear stress. As we discussed, the importance of hoop stress is unique to asymmetric problems and plays a dominant role in pressure vessels and cylinder structures. It arises due to circumferential expansion and must be accurately computed to ensure structural safety. Now, formulation of equivalent nodal loads. External loads are transformed into equivalent nodal loads using shape functions. This transformation allows the loads to be incorporated into the finite element equations. Consistent load vector estimation ensures the equilibrium of the element under applied loads. Then calculation of stresses in the elements. Stresses are computed from nodal displacements using the constitutive matrix and strain displacement relations. The strain at any point within the element is derived from the shape function and nodal displacement. Post-processing it involves evaluating stresses at specific points or across the entire element. Now, analysis versus numerical approach. The numerical integration like Gaussian quadrate is commonly used to evaluate load vector and stress integrals efficiently. The inclusion of the 2 pi r term in numerical integration is crucial for correct force and stress estimation. Analytical methods provide closed form solutions for simple geometries and loadings. Numerical methods such as a finite element analysis handle complex geometries and loading efficiently. Combining both approaches enhances the accuracy of load and stress estimations. Practical considerations and assumptions. Assumptions like material linearity and small deformations simplify the analysis. Accurate modeling of boundary conditions is crucial for reliable results. Mesh refinement and proper element selection improve the precision of load and stress estimation. Application in engineering design is estimating loads and stress in asymmetric components is vital for pressure vessels, pipelines, and tanks. Proper analysis ensures safety, durability, and compliance with design standards. Engineers utilize these methods to optimize materials and structural configuration. Conclusion and future directions. Accurate estimation of load vectors and stresses is fundamental for axisymmetry structural analysis. Advances in computational methods continues to improve analysis efficiency and precision. Ongoing research aims to incorporate nonlinear behavior and complex loading. For more realistic models, the estimation of load vectors and stresses for two-dimensional asymmetry elements is a fundamental aspect of finite element analysis for rotationally symmetric structures. By incorporating circumferential effects through appropriate mathematical formulation, axisymmetric elements provide accurate displacement and stress prediction with significantly reduced computational efforts. Thank you for giving this opportunity.